In this lecture, we learn about the definitions of products and co-products, which are the first sort of definitions by universal construction in category theory. Now, the idea behind products is the Cartesian product of sets. So recall that if you have two sets, A and B, then A cross B is just the set of all pairs, ordered pairs A comma B, where A is in A and B is in B. And this set comes with two projection functions. So I'll just visually draw it like this. A cross B to A, there's a projection function called P subscript A, and from A cross B to B, there's a projection function called P subscript B. And these are defined by P subscript A of A comma B is A, P subscript B of A comma B is equal to P. Now these projection functions give rise to a nice correspondence. So there's a bijective correspondence between the set of all functions from C to A cross B. And the set, well, the product of sets, f is a function from C to A, maybe I'll call it f subscript A cross f subscript B, C to B. Namely, given any function f from C to A cross B, I can map it to f sub A, which is defined to be P subscript A circle f, comma f sub B, which is defined to be P subscript B circle f. And conversely, given any pair f sub A, comma f sub B, I can associate to it a function which takes C to f subscript A, C, f subscript BC. So f subscript AC is an element of A, f subscript BC is an element of B, so this is an element of A cross B. And this is a bijective correspondence. Somehow in category theory, this kind of a correspondence captures the essence of products. So the game is somehow to take the notion of a product and rewrite it in such a way that we do not talk about elements of sets, but we only talk about objects and arrows. We would like to rewrite the notion of a product purely in the language of category theory. So let's do that, and that definition is the category theoretic definition of product. So let A and B be two objects in a category C. Then their product A cross B is an object. Well, maybe I should say their product is an object A cross B in C, which comes together with two projection maps. So I'll just two arrows together with arrows. And I'll use diagrammatic notation. So I'll just say A cross B, we have an arrow P subscript A and P subscript B. This goes to A and this goes to B. Okay, such that for every object C of the category C, along with arrows f subscript A from C to A and f subscript B from C to B, there exists Now let me explain this whole thing diagrammatically. there exists, so I'll draw this like this. So we have A cross B, we have P subscript A, the projection onto A, we have P subscript B, projection onto B. I'm using the words projection and so on, but remember A and B are no longer sets, they're just objects in some category. Okay, and A cross B is again an object, and these are just some arrows in the category. And we have this object C, and we are given functions from F subscript A from C to A and F subscript B from C to B. And what we want to say is that there exists a unique function F from C to A cross B. So let me write it out explicitly. There exists a unique arrow. I'll just write it here. Arrow F from C to A cross B such that P subscript A circle F is equal to FA and P circle B, P subscript B circle F is equal to FB. Now these conditions are more easily visualized in this diagram here on the right. What we are saying is, in this diagram, you go from C to A, there are two possible paths. One path is to go directly from C to A using the arrow FA, and another possible path is to go from C to A via A cross B. And so the arrow involved here is P subscript A circle F. And what we are saying is that both these arrows are equal. So P subscript A circle F is equal to F subscript A as arrows. This is an equality in arrows from C to A. And similarly, P subscript B circle F is equal to F subscript B. Okay, so what we're using here, we're relying very heavily on a diagrammatic notation. Let me just explain this a little bit. So a small digression before we go back to talking about products. Diagrams. So a diagram in a category C is a directed graph. And in this directed graph, multiple edges between nodes are allowed, and multiple loops are also allowed. Where each node of the directed graph is labeled by an object of C, and each directed edge from a node labeled by so it will be labeled by some object, say by A, to a node labeled by B, is an arrow in the category C from A to B. So this picture here is certainly such a diagram. It's a diagram. It has 4 nodes. They're labeled C, A, B, and A cross B, and it has 5 arrows: F subscript A, F subscript B, PA, and PB. And we say that the diagram commutes if well, so given any two nodes in this diagram, there are many different ways to go from one node to the other. So you can take a path and you can compose all the arrows along that path. And the resulting arrow from C to A is independent of which path you chose. So commutes if given any two nodes, the nodes say labeled A and B, the arrow A to B obtained by composing all the arrows along the path is independent of the path. Okay, so in this picture, for example, we have that if you take all the paths from C to B, well, there are only two paths. We have to take directed paths, one going directly from C to B and the other going from C to B via A cross B. This path from C to B, directly from C to B, just gives rise to the arrow FB, and this path gives rise to the arrow PB circle F. Okay, so this is probably easier to understand on an intuitive level rather than writing long definitions. Nevertheless, let me just explain why we use the nomenclature commutes. So it comes from a very simple diagram. So suppose I have objects A, B, B and C, and I have arrows maybe I'll call it F and G. F is an arrow from A to B and G is an arrow from B to C. And well, this is not going to work so well. So what I need is now let's take all these nodes to be the same. So I have A to A, A to A. This is probably the right way to do it. And I have G and I have F. So if these are all arrows, then this diagram commuting means that G circle F is equal to F circle G. So the arrows F and G, which are both arrows from A to A, they commute. And this gives you some intuition for why this is called commuting. But of course, it's a much more general phenomenon. So coming back to the definition of a product, I can try to rewrite it as there exists unique F from C to A cross B such that this diagram commutes. So such that this diagram commutes. So that we can take to be the definition of the product of sets. And in the category of sets, the product is just the Cartesian product as explained in this example which we did before even talking about the category theoretic definition of products. So example 1, maybe the motivating example is that in the category set of all sets, A cross B is the Cartesian product of two sets, and PA and PB are the projection functions. Now this definition of product is a bit like the definition of an initial object. We'll see this in a moment. So the first result that we'll prove about the product is that it is essentially unique. So here in the definition of product, we've said it is an object A cross B, which doesn't rule out the fact that there may be many ways of constructing the product. But there is a sense in which this product is unique. So let me formulate the statement carefully and then prove it. So this is the uniqueness of products. So the statement is the following. If we have two different products, so A cross B, remember product comes with these projection maps, PA comma PB, and let's say we have another notion of product, A star B. So this is a different object in the category possibly, and we have maybe projection maps which I'll call QA comma QB, are both products in a category C of the objects A and B. Then there exists a unique isomorphism phi from A cross B to A star B such that, and now this is best explained in terms of a diagram rather than writing down equations. So we have this one product A cross B, and we have projection maps PA to A, PB down to B. And we have another notion of product which we call A star B, and we have projection maps QA and projection map QB. So then the assertion is that there exists a unique isomorphism phi such that this diagram commutes. In other words, you can go from A cross B to B either by PB directly, or you can go via A star B. So what this commutes is saying, let me just spell it out again since these are new concepts. So commutes means one, that QB circle phi is equal to PB, and secondly QA circle phi is equal to PA. So these are the two assertions being made here. Okay, so that's the statement of the uniqueness of products. And now let's go on to prove this. So the proof is more of a performance than something we write down here. So let's see. So we have A cross B, and we have these projection maps, P subscript A to A, and we have a projection map to B called P subscript B, and then we have A star B, and we have the projection map Q subscript A, and we have projection map Q subscript B. And what the universal property or the definition of the product says, that the fact that A star B is a product, then we can take C to be this object A cross B, and we can take FA to be PA and FB to be PB in the definition of the product. So since A star B, QA, QB is a product, there exists a unique arrow phi, which goes from A cross B to A star B and makes this diagram commute. Now let's go one more step. let's go back to A cross B here, and A cross B has arrows to A and to B, namely PA and PB. Now, because A cross B is a product, we can take C to be A star B in the definition of product, and F subscript A to be QA and F subscript B to be QB. So then the universal property of the product says that there exists a unique arrow psi from A star B to A cross B, which makes this diagram commute. So the universal properties of this whole diagram, commutative diagram, comes about because of A cross B and A star B both being products. Now let's consider a slightly different diagram, a simplified version of this. So we have A cross B, we have PA to A, and we have to B, we have PB, and we also have, well, PA and PB. Now, the universal property for the product applied to the product itself. So now we are doing this, applying the universal property of the product by taking C to be A cross B itself and taking FA to be PA and FB to be PB. So the universal property implies that there exists a unique arrow from here to here, right? Which makes this diagram commute. But if we take here identity of A cross B, then surely this diagram commutes, right? So what we have is PA circle identity of A cross B, well, that's just PA, and PB circle identity of A cross B is PB. That's how identities work. But on the other hand, from this diagram, we also see that this diagram commutes if we put here, instead of identity of AB, we put psi circle phi. So this diagram here commutes whether you put psi circle phi or whether you put the identity of A cross B. Now by the uniqueness, this implies that psi circle phi is identity of A cross B. So from this diagram implies that PB circle psi circle phi is equal to PB, and PA circle psi circle phi is equal to PA. Comparing these two, we get identity of A cross B is equal to psi circle phi. And in a similar manner, where we would interchange the roles of A cross B and A star B in this diagram, we would be able to show that phi circle psi is also the identity of A star B. And therefore, psi is, or do I want phi? Phi is an isomorphism. It has an inverse, namely psi. And of course, it's unique because of the universal property. We already see that it is unique here because it's defined by the universal property. So it has to be unique, subject to this part of the diagram commuting. But that uniqueness is just coming from the universal property. So that concludes the proof of the uniqueness of the product. Okay, so it's not just saying that the object A cross B is unique, it's saying that the triple A cross B together with the arrows P subscript A, P subscript B is, well, it's not unique. There could be different objects with this property, but those objects would be isomorphic via a unique isomorphism. And this is just like, it's a slightly more complicated situation, but it's like the situation we saw last time where we said that an initial object in a category is, any two initial objects in a category are isomorphic via a unique isomorphism. Let us look at another example of a category where products exist. Let's look at products in the category of rings. So recall that a ring is an algebraic structure with two binary operations, addition and multiplication. Under addition, it forms an abelian group. Under multiplication, it forms a monoid. And these two algebraic structures are related via distributivity laws. We have always insisted that rings be unital. So there's a multiplicative unit in every ring. And the arrows in the category of rings are ring homomorphism. So they preserve addition and multiplication, but also they must map the unit of the domain ring to the unit of the image ring. So that's the category of rings. And in the category of rings, there is a well-defined notion of product. So given two rings R1 and R2, you can take the Cartesian product R1 cross R2 and endow it with the structure of a ring using component-wise addition and multiplication. Okay, so you have R1 comma R2 plus S1 comma S2 equals R1 plus S1 comma R2 plus S2, and you have R1 R2 dot S1 S2 is R1 S1 comma R2 S2, and this gives rise to a ring structure on R1 cross R2. Note that the unit of R1 cross R2 is the unit of R1 comma the unit of R2. So you can check that all the axioms for a ring are satisfied by this product structure on R1 cross R2. And you have the projection maps, the set theoretic projection maps P1. So let's draw it like this. Always prefer diagrams while doing category theory. It's easier to see what's happening. B, the set theoretic projection maps. And those you can easily check are ring homomorphisms because addition and multiplication are defined component-wise, and because the unit of R1 cross R2 has each component the unit of R1 and the unit of R2. So now what we know is, so now we need to prove the universal property for a product, that is the definition of a product in the category of rings. So given a ring R and F1 R to R1, F2 R to R2, we need to show that there exists. So let me draw the diagram that we are after. So we have R1 cross R2, we have P2 down to R2, we have P1 down to R1, and we have this ring R, and we are given F1 and we are given F2. So now this R1 cross R2 is a set theoretic product. So because it's a set theoretic product, we know that there exists a unique function, not yet a ring homomorphism, a function. There exists a unique function f from R to R1 cross R2, which makes this diagram commute. So there exists a unique f, but f is only a function so far. And now all we need to do is to check that f is a ring homomorphism. But remember, f is defined by f of r is equal to f1r comma f2r, and it is easy to check that f is a ring homomorphism. I will not bore you with those details. You can work them out yourself if you feel the need. Every concept in category theory has a dual, just like the dual of the concept of an initial object was a terminal object. So similarly, there's the dual of the notion of a product, and it's called a coproduct. So let's define it. And a coproduct is defined as given two objects A and B, in a category C, their coproduct is an object. We'll write A plus B together with. Now the idea with dualizing in category theory is that the directions of all arrows are reversed. So together with arrows, and so now we have, earlier we had A and B, A cross B to A and B, and now what we have is A plus B here, and we have arrows from A to A plus B, which we'll call this JA, and we have another arrow B from A B to A cross B, JB, such that for any object C, and arrows F A from C to A to C, and FB from B to C. So now if you go back to the definition of a product, we are reversing the directions of all the arrows here. So earlier we had arrows from C to A and C to B. Now we have arrows from A to C and B to C. Let's draw the diagram that we want. So it will be the reverse of the diagram we had in the definition of the product. So we have A plus B, we have an arrow going from A into A plus B, which is J subscript A, and we have another arrow from B into A plus B called J sub B. And we also have an object C, and we have arrows F subscript A from A to C, and another arrow F subscript B from B to C. Okay, so then what we want to say is that there exists a unique arrow which we will call F. There exists a unique arrow F from A plus B to C such that the above diagram commutes, which can be written in longhand as F circle J sub A equals F sub A, and F circle J sub B equals F sub B. This is the definition of a coproduct in a category. Okay, so it's exactly the definition of a product, but with the directions of all the arrows reversed. And now, just to see if you were following what I did before with products, I will give you the following exercise. Formulate and prove the uniqueness of coproducts. Okay, in general, coproducts or products may or may not exist, but when they do exist, they are unique in a certain sense. So what you have to do is you have to figure out the analog of the uniqueness statement of products for coproducts. Okay, let me give you an example of coproducts. Pretty much everything in category theory, we try to see what happens with the category of sets. So in the category of sets, the given sets A and B, their disjoint union A disjoint union B. That means you take A and B, even if you have common elements in these sets A and B, you take the common elements, you treat them as different elements. So maybe you make a copy of all the elements which they share in common and create disjoint sets A union B. So the cardinality of the set will be the cardinality of A plus the cardinality of B. With JA being the inclusion map, so JA of A equals A, which is an element of A union B, and JB of B is B, which is also an element of A union B. Note that we have this universal property, so let's just check that this meets the criteria for being a coproduct. So we have A disjoint union B, we have JA, we have JB from B, and now what we are saying is that given any set C together with functions FA and FB, now we are in the category of sets, so arrows are just functions, there exists a function F, a unique function F, and indeed this function F has to be given by so let's just define it like this. Maybe it's better to write it like this: f of x is equal to f subscript A of x if x belongs to A, and it's equal to f subscript B of x if x belongs to B. And this is the only function that will do this trick for us. So in the category of sets, the coproduct is just the disjoint union of two sets. So we have seen the definition of products of two objects in a category and coproducts of two objects in a category, but we can generalize these definitions further to arbitrary families of objects. So products of families. So the definition is as follows: given a family AI, I indexed by some set I of objects in C, their product is an object which we denote by, we use the pi notation, the product notation which we use while multiplying numbers and so on, together with arrows pi from product I in I, AI to AI, such that And now we more or less follow the definition of a product. So we say that whenever we have an object, for any object C, together with arrows Fi from C to Ai for each I in I, there exists a unique arrow F from product Ai to this product, from C to product, such that, okay, so maybe it's better to draw a picture here. So we have the product I belongs to I, Ai, and we have these projection maps, arrows to Ai, and we have an object C, and we are given a family of arrows from C to Ai called Fi. And the assertion is that there exists a unique arrow from C to the product, which we will call F. This diagram commutes. Okay, in other words, we are saying that Pi circle Fi, oops, no, not Pi circle Fi, Pi circle F is equal to Fi for all I. So we want to say for all I in I, this diagram commutes, for all I in I. And you can check that in the category of sets, again, the product is the Cartesian product of a family of objects. And similarly, you can define a coproduct of an arbitrary family of objects. It's the same kind of definition. So we usually call it summation I, the coproduct, same notation as before, summation I in I, Ai. So maybe I should say is an object together with arrows Ji from each Ai. There's an arrow Ji to this coproduct. I belong to I, Ai, such that for every object C, and arrows Fi from Ai to C, there exists a unique arrow F from this coproduct to C. So let me draw the diagram. So we have Ai, and for each I we have this Ji, I in I, summation Ai, and we have this object C, and we are given, for each I we are given an arrow Fi, and the assertion is that there exists a unique arrow F, which makes this diagram commute for all I. Okay, and again in the category of sets, this coproduct is the disjoint union of this family of sets. Let us end this lecture with a slightly different kind of example of products and coproducts. So let X be the set, X be any set and P denote the partially ordered set of all subsets of X. Okay, so partially ordered by inclusion. Then we have this category script P. In this category, objects are, so we've discussed this category before. Objects of P are, in this specific case, subsets of F of X, and given subsets A, B, there is a unique arrow. So let's just write it down. CAB is either is a singleton set. Maybe we'll call it arrow from A to B if A is contained in B and it's empty otherwise. So this is a special case of the general category that we associated to a general, the category that we associated to a general poset. Specialized to the case where the poset is the set of all subsets of a given set X. And here's an exercise for you. Prove that in this category A cross, well, we could do it in general. I in I, AI is just the intersection I in I, AI, and the coproduct I in I, AI is just the union I in I, AI. And here I don't mean disjoint union, they're just subsets of the set X. You take their union inside X. And so that's again a subset of X. So it's just an exercise in, and if you can solve this, then you would have to some extent grasped the definition of product and coproduct that I gave you in this lecture.